All right, so what about these extrasolar planets? What are they? So let's just talk about a little bit of review to kind of set the stage for extrasolar planets. So, just to review, the space between the stars that is filled with a very thin amount of gas and dust, which are the remains of dead stellar interiors, is called what? So pause the video, think about it, and then hit play again. Hopefully you answered the interstellar medium, which is that thin layer of gas and dust. What is the most abundant material in the universe? All right, hopefully you answered hydrogen. If you answered helium, you're close, but really hydrogen is the most abundant, then followed by helium. So why do I bring these two conceptual questions up before we talk about extrasolar planets? Well, I just want to remind you that we believe our solar system formed in a nebular gas region, which is what we call the nebular theory for the formation of our solar system. The idea that a cloud of gas and dust was slowly rotating and collapsed into a disk where the center formed a protostar, which eventually turned into the sun, and a disk of gas and dust surrounding it formed into the planets. And what we know is that this is not unique. We see this all over the place. So for example, here are some extrasolar planets forming where we see a galactic disk with a center protostar forming around it. Okay, so the basics, right? This formation of the solar system, we are always revising this idea as we look for other planetary systems. So an extrasolar planet is just a planet or a planetary system, a solar system, going around another star. Because remember, our sun is just a star. So the same basic theory applies, that we think that these extrasolar planets formed from a gas cloud condensing and rotating, flattening into a disk, that central star being born and the disk of gas and dust surrounding around it is what formed the planets. Now the question we want to know is, are planets that are formed around other stars similar to Earth? Do they happen to be in what we call the habitable zone where life could form? That's what we're studying when we're looking for extrasolar planets. What are these planets like around other stars? So just to review, what is the difference between a protosun and a sun? When does that protosun become a full-fledged star? So go ahead and pause the video and think about it for a second. All right, hopefully you answered thermonuclear fusion began at the center. It's only at this point is the star really a star. It's creating its own energy. So once that happens, we can have the solar system become fully formed and have extrasolar planets orbiting around a star other than our sun. So to really kind of get a clear idea of what extrasolar planet systems might look like, let's consider our own system a little bit further. So most of the planets in our solar system orbit the sun on or close to what? The ecliptic plane. Now, the ecliptic plane, as we've been talking about in astronomy, is based on the sun and the planets, right? Well, there's an ecliptic plane to any solar system, and what we notice is that most planets orbit in about the same plane around their sun, just as our planets orbit around our sun. That ecliptic plane is really just a result of the flattened protoplanetary disk forming around a new sun or a new star. So, to really wrap that all together, so extrasolar planets are planets orbiting other stars. So we have solar systems that are forming around other stars. Those planets tend to rotate in the same direction and lie in a disk, just like our solar system does. What we found, though, is that a lot of the extrasolar planets that we have found are quite massive and have orbits quite close to the sun. It's only been in the last 5 years or so that we've actually been finding planets that are a little bit smaller, more Earth-like, and some that are orbiting in orbits similar to Earth's. But really, a majority of the planets we've been finding are a little bit different than we originally thought they might be. So how are we finding extrasolar planets? There's three basic methods that we're using to find extrasolar planets. The first one is called radial velocity, or what I sometimes call the wobble of the host star. The second method is called the transit method, and the third method is called microlensing. So let's go through each of these. Okay. So to give you a visual overview, so radial velocity or the wobble method. So go back to what we learned about Newton and gravity. Remember when two bodies are orbiting, one body is orbiting another star, for example, that these bodies are gravitationally tugging on one another. So for example, the sun is tugging on the planet, but remember that the planet is also tugging on the sun. So if we're looking at a star and we're looking at its spectrum, we're able to see if that spectrum is coming at us or away from us. And if it's moving back and forth, it's quote-unquote wobbling, we know that something is causing that star to gravitationally shift. And usually that means that there's a planet orbiting around that star. So here's what this would look like from Earth. So let's say here's our telescope, and we're looking at a star. We don't see this planet because it's too small to see, but we can see the star. And what we notice is that the starlight is sometimes coming at us, okay, meaning it's blue shifted, and sometimes it's moving away from us, which means it's red shifted. This back and forth shift or wobble of the star indicates to astronomers that the planet is gravitationally tugging on the star. So when the planet is over here, it's pulling the star away from Earth. And when the planet is over here, it's tugging the star close to Earth. So the star is literally being tugged by this planet, and we are seeing the motion of the star. That's the radial velocity or the wobble method. So the second method was called the transit method. This is when the planet orbits right between our line of sight, between us and the sun. So what that means is it's going to block out some of that star light from what we see. And we see a dip in the decreased brightness of the host star. That's the transit method. Oops, sorry, here we go. Here's the transit method. So when the planet moves in front of the star, okay, we are going to see a dip in brightness. That dip in brightness tells us quite a few things about that planet. It can give us an indication of the size of the planet. And by looking at some spectroscopy, we're also able to look at what the planetary atmosphere might be like. So we can learn a lot of things. Now, the only problem with the transit method is it has to be in the right orientation, right? If you had a planet orbiting like this, it would never cross the host star. So we're only able to find extrasolar planetary systems that are moving in an orbit that is aligned directly with our line of sight. So already with that, you can see that this detection method is somewhat limited. Okay, and the final method of detecting extrasolar planets is what we call microlensing. Again, this is using gravity and the warping of space-time and how we view a star behind the star that we're looking at. Okay, so let's look at this in a bit more detail. So for example, here we are in our telescope on Earth, and we're looking at this distant star. Okay, let's say we notice this star here. This star here we see might actually appear to look bigger because it's bending the space around it. And when we're looking at this star in the background, it's going to appear bigger to us because of the gravitational pull of this star. Well, if there's a planet in the system as well, that lensing is going to have an even bigger effect. So effectively, a star with a planet around it is going to act like a lens for us, a magnifying glass, where it's going to actually make the image of this distant star even bigger. So that's the kind of very crude basics of microlensing. So I just kind of wanted to go into a bit of the most recent work that scientists have done in terms of extrasolar planet detection. So the Kepler Space Telescope was on a mission to find extrasolar planets. And Kepler Space Telescope did a lot of work from 2009 to just recently in 2018. Kepler primarily used the transit method to detect extrasolar planets. So it was looking for a planet that's going to move in front of the host star. And the Kepler mission showed us that there are small rocky planets orbiting the habitable zone. This is very exciting for us. So really, every star we see has on average one planet, and Kepler Space Telescope was the one to really show us that. So let's check out a video on just kind of the basics of the Kepler Space Telescope mission.
For thousands of years, mankind has wondered, are there planets around other stars? Is there life out there? But we didn't know. We didn't know if there were any planets around the stars.
0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Before the launch of Kepler, most of the planets we knew about were really big planets like Jupiter. But Kepler was so sensitive that we started finding smaller and smaller planets. We discovered planets smaller than had ever been discovered before, and just many of them, indicating that the galaxy's full of planets. Crazy worlds that we didn't predict, things that we hadn't imagined. We find planets orbiting so close to their parent star that the star-facing side has temperatures in excess of that required to melt iron. These planets have an entire hemisphere that's like a liquid ocean, but it's not an ocean of water. It's an ocean of molten rock. We see planets that are orbiting not one, but 2 stars. That is, if you look in the east, you'd see not 1 star rise, but 2.
Almost all the astronomers that I know grew up reading science fiction. That's why a lot of them got into the business of looking for planets in the first place, to find out if any of this, fantastic speculation that inspired us could be true. And now we find out that, it could be true.
We learned from Kepler that the most common types of planets in the galaxy are unlike the planets in our own solar system. These worlds are intermediate in size between the Earth and Neptune, but we're not exactly sure what they're made out of.
What are the things that we know now that we didn't know then? I mean, things like planets are ubiquitous. Planets are diverse. The stars that we find planets around are diverse. The systems that planets live in vary widely.
It was breathtaking to see all of the planets come rolling in from this exquisite data over the years that we were collecting data with Kepler. In the end, we found dozens of small, potentially rocky worlds orbiting in the Goldilocks zone of their stars, that distance at which you can have liquid water pooling on the surface of the planet, capable of supporting life as we know it.
The science value of the collected data spans almost every field of astronomy and planetary science. It revolutionized not just exoplanets, not just stars, but a large number of the scientific fields of astronomy today.
There's one summer I worked in an observatory, and I would go outside at night and look up at the stars and just be blown away at how vast space was. And I actually felt a little lonely. And when I go out and look at the night sky now, rather than being awestruck by the vastness, I'm awestruck by the possibility.
There aren't that many opportunities in life where you get to participate in a project as important as Kepler is, that answers such a fundamental question that we've been asking ourselves for so long. Now we know when we look up into the night sky that every star we see has on average at least 1 planet, and that many of those planets are similar in size to the Earth and a chance for life as we know it elsewhere.
Searching for life elsewhere is one of the key themes that drive our science portfolio. And at the center of that is Kepler. New missions, like the Transiting Exoplanet Survey satellite TESS and the James Webb Space Telescope, will build on Kepler's success and take our search for life to new heights.
It has been extremely gratifying to see the data come back from the mission and show what we wanted to know, give us the answer. Many stars have planets. A lot of these planets are Earth-sized. That's Kepler's legacy, this new knowledge that we have about planets around other stars.
Okay, so that just gives you a little overview of how awesome the Kepler mission really was. The video mentioned TESS, the Transiting Exoplanet Survey. That project is already giving new data. Astronomers are starting to analyze the new data from the TESS survey as well, and we're still waiting for the James Webb Space Telescope to launch and start taking data. So one of the great systems that Kepler found that's pretty well known is the Kepler-20 system. There's a few other Kepler systems out there, but I just wanted to highlight this one because this is what the video kept talking about Kepler's mission was the first to really show us that it's not just those huge Jupiters orbiting close to the suns, but that there are some other planets orbiting stars that are more like Earth-sized. Okay, so for example, Kepler-20e and Kepler-20f. So let's check out this short video that tells you a little bit more about this Kepler-20 system and how the Kelper Space Telescope was finding Earth-sized exoplanets.
NASA's Kepler mission has confirmed the discovery of the first Earth-sized planets outside our solar system orbiting a sun-like star. Located about 1,000 light-years from Earth, the Kepler-20 solar system has 5 planets orbiting a star similar to the Sun. Kepler-20f, the 4th planet in the system, orbits its star every 19.6 days and has a surface temperature of 800 degrees Fahrenheit. Kepler-20e has an orbital period of 6.1 days and has a surface temperature of 1400 degrees Fahrenheit. It is about 90% the size of Earth. Kepler-20f is slightly larger than Earth, with a radius that is 3% larger. The extreme temperatures and proximity to their host star means that the planets are not in the habitable zone, the region where liquid water could exist on the surface. These discoveries are a validation of the complex data analysis process that the Kepler team is using to detect transits of Earth-sized planets in front of their stars. Scientists hope to eventually find Earth-sized habitable planets with liquid water that could sustain life as we know it. Kepler is on a 3.5-year mission to search for Earth-sized planets in our galaxy.
So clearly, Kepler went longer than the 3 years that it expected to go. So back to this idea that we were starting to find Earth-sized planets that possibly are in the habitable zone, which means we can't see these planets close enough to see what they're really like, meaning that these images that you see here are artist renditions. We don't quite know if they have water or atmospheres or things like that, but it's our first clue. Kepler really gave us the first clue that there's planets around almost every star we see in the night sky, and that was huge. Okay, and these systems being within that habitable zone is just the zone around a star which is close enough but not too far away that an Earth-like planet could orbit and potentially host life. And we have this habitable zone based on our sun, okay, size and heat output, and where our Earth's location is. And then, of course, that habitable zone might vary a little bit depending on whether that sun is smaller or not outputting as much energy, or bigger and outputting more energy, right? If it's smaller and not outputting as much energy, the habitable zone might move inward. If it's a bigger star giving off more energy, that habitable zone may move farther out. So it does vary based on the system, but it is based on our understanding of what we know one planet in the universe for sure has life, Earth. So which other planets might exist in that region that has created our own Earth? And that's what we call the habitable zone. So another system that has been recently discovered that has really excited scientists is called the TRAPPIST-1 system. So TRAPPIST-1 is an extrasolar planetary system, and TRAPPIST is really the telescope that discovered the system. Okay, so this system is located 12 parsecs away from our solar system, and it's in line with the constellation Aquarius. So if you went out and you looked towards the constellation Aquarius, you'd be in that segment of the sky. Now, the star at the center of this planetary system is 12 times less massive than our sun, and it's just slightly larger than Jupiter, so it is a small star, okay? But what's neat is that all of the planets that in this system transit the star, so that it passes in front of the star. So we were able to detect this system using the transit method. And what's even neater is that the planets have sizes and masses comparable to Earth, which is what really got scientists excited. So here's an artist rendition of all of these planets within the TRAPPIST-1 system. Okay, and these are ideas of what they might look at because they are Earth-like in terms of mass and size and location. But again, notice that TRAPPIST star is much smaller than our sun, okay, and redder. Okay, it's probably a lot older and probably not outputting quite as much energy. So you might, again, recall that that habitable zone probably shifted a little bit closer to the TRAPPIST-1 star. So let's take a look at this video to give you an overview of the TRAPPIST-1 system.
The big news is that around a very nearby, cold, small star, we found 7 rocky, Earth-sized planets, all of which could potentially have liquid water.
For me, it's mind-blowing. The first time I saw what the system had in it, I just was like, you gotta be kidding me. And then I looked at the data myself, I'm like, yeah, there they all are. It's just, I would have never predicted this. It's beyond, anything I could have ever dreamt of.
I felt super excited, amazed by the existence. The very existence of the system was kind of shock.
If you were standing on one of these planets, you'd actually see a lot of them sort of in the sky, whipping by on these very short orbital periods.
It is not launching in 2018.
It is an excellent, fantastic discovery.
All right, so you can see that that is just really cool, right? That TRAPPIST system is really showing us that there might be these Earth-like planets in the habitable zone. And we don't know what the planets are really like yet. We're just speculating. But again, it's just really exciting to see that we are finding planets around other stars that might be similar to Earth. So that question of, is there life in the universe? I think, hopefully, yes, right? That's my hope, at least. So let's do a bit of review before you finish up this section. So here's a few questions for you. So again, after I read the questions, pause the video to think about them. The overall shape of the orbits of most of the planets in the solar system is what? All right, hopefully you answered slightly elliptical but nearly circular. And we are seeing this similar trait around these extrasolar planet systems as well. Here's another review question. Which of the following general statements about all of the planets in the solar system are true? They orbit the sun in the same direction. And again, we are seeing that with most of these extrasolar planetary systems as well. And then finally, in order to produce a planet-wide magnetic field, a planet must have in its interior some material capable of carrying the electric current to produce what we call the dynamo effect. All of the following substances would appear to fill this role except one. Which is the exception? Solid iron. So recall that when we see magnetic fields around other planets, that tells us that we think that the material is molten or fluid. Okay, so molten iron could definitely produce a magnetic field. Liquid metallic hydrogen we think is what produces the field on Jupiter and Saturn. Even a liquid ammonia water mixture under high pressure could definitely produce a dynamo effect, let's say on Uranus or Neptune. It's really the solid iron that really we don't think can produce this magnetic field. All right, so that concludes our studies of extrasolar planets.